Hey folks, how you doing? We're on day 14, walks and trees. Let's go ahead and get started. We've seen this definition before, but I just want to remind you that a walk is a sequence of vertices that allow in which every adjacent pair of vertices in the sequence is forms an edge. So this sequence, B to D to B to C to D, is a walk. It's not a very efficient walk. We are going from B down to D, then back up to B, then down to C, and then over to D. But that's perfectly allowed. We're allowed to go back and retrace our steps and go back to other vertices. This is a walk in this graph. Okay? A circuit is a walk that starts and ends on the same vertex. So if we come back to the same point, it's a circuit. So DAC, BAC, and then D. That's a circuit. The length of a walk is the number of edges, which is one length than the number of vertices. If I count this is 1, 2, 3, 4, 5, 6, 7. But even though there are 7 things in this set here, that's 6 edges. The first edge goes from D to A. Second edge goes from A. Third edge goes from C. Fourth edge goes back to A. The fifth edge goes. So the length is one less than the number of vertices. We're actually counting edges. Okay? So this is a circuit of length 6. So here's an example out of the book. Let's give examples of walks from length A to E. Lengths 1, 2. Well, length 1, we have no choice. From A to E. Length 2, we have to go from A somewhere else and then go to E. 2 ways of doing it. A to F, and or we can go from then from length 3, I want to go from A to another vertex to another vertex. So we can go from A to F to E, or from A to F to C to E. There are 2 other possibilities. You can go from A to C back to A, from A to F, and so there are actually 4 different paths from A. I think that's all. So that there is no walk from A to G. If I try to walk from A, there's no way that I can get from A to G because A has only F is name. He has only AE. He has AC. Finally, F has only. So these 4 vertices, the edges that connect them, are a
entirely separate component from the other vertices. There is no edge that allows me to get off of the F graph. ACF component is not. All right. Same graph. Identify the components of G. Well, we've just identified one of them, F. The other component then should be H. We can verify that they form a component because B can reach all of the other three. So we have two connected components. All right. Let's move on to a different example. Prove that being in the same component is an equivalence relation on the set of vertices. So let's review what an equivalence relation is. An equivalence relation reflexive, metric, and transitive. So we need to show that being in a component satisfies this condition here. So we have to prove all three things. Let R be Y, then R, Y, R same component. So these three. X be component containing X is the component containing X. That sounds funny. What I want to show is X is related to itself. So that the component that X is in, or the, well, that's sort of obviously true. And so R is reflexive. To show reflexive, we start out by just assuming one
Vertexes.
G. So symmetric, we start out by assuming two vertices at X and Y. And we already get to assume that X, Y is in R. So let Y and X and Y are in the same component. So there's the walk Y. But taking that sequence of vertices and just reversing it gives me a walk from Y to X. Reversing this X, so also in R. So R. All right, we use a single vertex to show reflexive. We use a pair of vertices metric, three vertices to show transitive. X, Y, and Z. Y, B. Then we can walk from X to Y, and we can walk from Y to Z. Walk, Y, from Y to Z. What we want is a walk from X to Z. So if I can walk from X to Y, and I can walk from Y to Z, how do I walk from X to Z? So to Y, and then I just keep going to Z. Concatenation of those. X is barely fit that in. I hope that makes sense. So being in the same component is an equivalence relation. Reflexive relation, it's symmetric and transitive. Walk from X to Y, I can walk from X. I can walk from X to Y and from Y to Z. And I can always walk from X to X by taking 0 steps. Okay? All right. A walk that does not repeat the vertexes is called a path. A walk with a length of greater than 1, no vertexes, except that the first vertex is the same as all the site. I want to talk about this definition. So a path repeats no vertices. That's in the definition. A walk, a cycle, give you an example, looks like this. But if I write this out following the definition, that A to B to C, but I can't stop there because this is that. In order to write out the cycle, I have to specify that the edge from D back to A is part of the cycle. And so I'm not repeating any edges, but I do repeat the fact that I start and end on the same vertex. So this exception is what allows the cycle to be closed at the end. So but the point is I'm not doing this back over. Right? So paths and cycles are analogous to walks and circuits, but they can't repeat vertices. All right. So let G be a graph and U be vertices. If we have a walk from, then we also have a path from. So here's an idea. I can walk from U to V. even if that walk goes back and repeat, I can just take out the little section that looped back around, and the rest of this path. That's the idea. I want to be able to prove that I can always create a path from you. Cut. Done. Path. Or be a walk from you. Suppose not a path. Then some vertexes are I, J, less than J, not less than or equal, but in parentheses. One up through I, gets up to VI, go around the loop, and then this is the same as VJ. So since it's the same as VJ, I'm just going to keep on at VJ plus 1 now. J plus 1 up through N. Also a walk. Order. So this still may not be a path, because we may still have another loop somewhere later on that we have. I don't know for sure that this is a path either. But every time I remove these little edges, the path gets shorter, and there's only so short that it can get. At some point, I can't make the path any shorter, because once it's down to a length of 1, that's just an edge from you. Okay? So we can move vertex until bulk. At that point, we have. All right, let's keep going. Let G be a connected graph. Suppose that we have a cycle in which U and V appear consecutively. So I have a cycle. Here's U somewhere. And there may be more to the graph than that. This is sort of a picture. If I were to delete edge from U to V, then the graph is still connected. So remember, a graph is connected and walk from vertex. All right, so let's look at a proof. Let can't call them U A any two vertices minus then A and B also vertices. Since G is connected, NG from A. So in the original graph, before I deleted the edge from U to B, I was able to find some walk from A, no matter what vertices. So let's look at two disjoint cases now. Case one, that walk contains since it doesn't contain UV, then it's also a walk in G minus U. But what if the walk that we found in G does contain? Then what I'm going to do is I'm going to delete this part of the walk, replace it with the remainder of the cycle. So that might require retracing a little bit. So this won't be a path, but we don't have to have a path. We just have to have a walk for the. So I walk up to U, I take a U-turn, and then come back around the other way around to V. So that's my other case. Case two, that does contain place complement cycle. That's either way, G minus U. So okay. All right. Two more slides. Let's keep going. A tree is a connected graph with no cycle. I can edges and vertices, but edges that create cycle back. So it looks like a parent and children work with trees before we have learned about specifically about particular types of trees. Binary tree. Nothing here that says this has to be binary. Any number of children for a specific vertex. Um, Perfectly. A leaf is a vertex of 1. A node that doesn't have has a parent but no children. If we have a tree, then deleting any edge of the tree disconnects the graph. If I delete a tree, if I delete an edge, um, let's say the vertices on the two ends of the edge are A to B, then I no longer have a walk from A to B. Because if I did have a walk from A, then that walk plus that edge would form a cycle. The tree doesn't contain. Let A be vertices adjacent vertices. Minus does not contain walk from because if it did, that walk plus A circuit. He can't have any cycles. So a tree, every single edge is vital to the connectivity of the graph. You can't not lose a single edge without losing part of the graph, making part of the graph. On the other hand, if I delete a leaf, a tree, remember the rule is if you delete a vertex, you also have to delete the edge that becomes orphaned as a result. And so what you have left is still a tree. So, all right. So what do we have to show? We have to show that, so let leaf go connected all right. All right. Let A and B vertices also. Since connected, their path. Need this to be a path, not a wall. from this path cannot contain the leaf that we deleted. Here's why. V has only a degree of 1. So if I am traveling along a path, I come to V, I've hit a dead end because I can't go back along this path because then I would repeat the vertex. Path cannot contain of degree 1. Path connected. He has no. Deleting a vertex doesn't create cycles. So those are two things that we have to show. It's connected, it has no cycles. No cycles is easy. I didn't have any cycles to begin with. I can add edges to create cycles, but I can't delete from something that has no cycles. Neither does T minus V. So minus. Okay. Our last definition for the day. Graph is bipartite if its vertices can be divided into disjoint sets x and y, such a way that every edge graph connects a vertex in x to a vertex in y. So informally, if you want to think about it, we can put the vertices onto two, and every edge connects a member from one team to a member of the other. I'll show you an example. This graph is bipartite. If I were to label my teams A and B, then this would be A, let's say, then it's got an edge to this vertex, so this vertex now has to be on. And now this vertex is connected to this vertex, so this vertex has to. You never connect two vertices. A is on a different team. This vertex and so then this vertex is on A, vertex is on T. Right? So we do not have any edges that connect to. This applies in like electrical and circuit design of considerations when we have to think about like positive and negative nodes on positive and negative. Don't want to wire two positive nodes together. That's another application. Well, what would break bipartite is if I had a vertex of team A connected to a vertex on team. This vertex was connected to, and then these two vertices also connected. Then I have a conflict with the last vertex. But that conflict comes around because I have closed off cycle. Cycle is odd length, so I can't go from A, B to A to B, A. I went from A to A, and So a bipartite graph contains no cycles on length. That's pretty easy to check. That means that all trees are bipartite. And why is that true? Trees contain no cycles at all. So they can't contain any odd cycles. Okay? So all trees are bipartite because the rule is a graph is bipartite if it doesn't have any odd cycles, and trees don't have any cycles. So all trees turn out to be. Okay. Uh, Thanks for bearing with me. We'll pick this up again on Wednesday. Have a great couple of days.